All right, geometers, welcome to this hopefully brief video explaining to you how it is we can derive the formulas for both the volume and the surface area of a sphere. So that's the purpose of this video, to help you to understand where these two formulas come from. And so let's begin. So I've got over here a quick reminder of Cavalieri's principle. And remember, the key with Cavalieri's principle is that he said if the cross-sectional area of two figures is the same and their height is the same, then their volumes must be the same. And so here we have a representation of that for a prism, but that principle, of course, applies beyond the realm of just prisms. Okay, so now we're going to move over to our demonstration over here. And again, what we've got to realize is that we are attempting to justify or demonstrate the formulas for volume and surface area of a sphere. So we're going to start off with this shape over here. And what we actually have here is a hemisphere. So we have half of a sphere, and then next to it we have a cylinder, and taken out of the cylinder we have got a cone. So keep in mind the formulas for the volume of a cylinder is going to be pi r squared h, so pi r squared for the base and h for the height. And for the cone, which we demonstrated before using Cavalieri's principle, the volume of a cone is going to be 1/3 base area times height. The base is a circle, so 1/3 pi r squared times h. Okay, so a couple of relationships first. The objective of this is we're going to use this cylinder that's had a cone removed from it in order to show you how to find the volume and in turn surface area of the hemisphere, which will then double in order to give you the formula for a sphere. Okay, first things first that you need to see, and that is that what we've got here, if I move this all the way up to the top, is that the length of the radius, so the length of the radius, which here is represented by x, but the length of the radius is the same as the length of the height, and so that should hopefully make sense to you. What we've got with a sphere is just a three-dimensional circle, and so if I were to put this radius in here, a radius to any point, that one went a little bit over, a radius to any point on the surface of a sphere must have the same length by definition, because the sphere is just a three-dimensional circle. And so we can establish over here that this r is the same as this radius over here, and what we need to understand, one of the key things to understand, is these two shapes have got the same height. Okay, and so that's the first of them, and then the next part is going to be this. So what you can see is as I move, change the height, and so as I'm changing the height, what we're attempting to look at is the cross-sectional area. And so I'm looking at the area of this disk, and I'm also looking at the area of this ring. Okay, and so that's going to be important. And so let's start with the first important connection to make, and that is that in both of these figures the overall height of the two shapes is the same, or of the two solids rather. And the second thing that we need to realize is as I'm moving the red dot down and I'm modifying the height, because of course each of these disks has got a different area, because as I'm moving up the radius is getting smaller, and as I'm moving down it's approaching its maximum value. But as I'm moving up, the heights of the two solids are the same. And so we've already taken care of one of the requirements for Cavalieri's principle, and that is that the heights must be the same and the cross-sectional area. So we've established that our heights are the same. We now need to focus on the cross-sectional areas. Okay, so let's begin with the proof. I'm going to focus initially on the hemisphere, and so at any given height h, we're going to look at the area of a cross-section of that sphere, or I beg your pardon, of the hemisphere, and that is going to be pi times x squared. And so this is of course a circle. If I take this and rotate that round, you can see of course we're dealing with a circular base. Okay, so let me reset that over there. And so we're dealing with a circle, and so we're just using the formula pi r squared. In this particular case, as we move up, x represents the length of the radius, r represents the original radius of the hemisphere, and so of course when I move down here, then x and r are the same. So for any other height, as we move up, we have this relationship for the cross-sectional area is going to be pi times x squared. And now we're able to substitute that with r squared minus h squared. What you should be able to see, and so I'll just jump over to the diagram over here. What we should be able to see, if I move to my other diagram, is that what we've got over here is we've got a right triangle. And because we've got a right triangle, of course, Pythagoras' theorem applies. R squared must be equal to h squared plus x squared. And that's why and where we can rearrange and substitute in here r squared minus h squared in the place of x squared. And so that obviously is a simple rearrangement of Pythagoras' theorem. Okay, so now we come back over here, and now we have this pi times r squared minus h squared represents the area of this circle. Okay, so let me put that back. And what I'm going to just do is reset that quickly and catch up over there. Okay, now what we're trying to do is look at the figure on the right-hand side. And according to Cavaliere's principle, if we can show that the area of this ring over here has got the same area as the area of this circle, then what we're able to prove is that the volume of the hemisphere will be the same as the volume of the cylinder minus the cone. That's how we're obtaining this ring. Okay, so let's begin. First thing we're going to do is the area of the cross-section of the solid. So the area of the cross-section of the solid, they're writing as pi r squared minus pi h squared. So let me clarify a couple of things there. First of all, I'm going to move all the way up to the top over there. This h is of course the same as this h, which is the same as r, and we've also got the same r in the base. And so a couple of key things that we need to realize in this diagram over here, this length over here is the same as this is r and this is r. So of course that length, when we are at the base, those lengths are going to be the same. Of course, when we start moving up and down, that's not necessarily true. This length of y definitely is not going to equal the base. But I do want to make that connection initially, because what we're talking about when we talk about the ring, and so for this ring, we're going to use the outer circle of the ring, and so the outer circle of the ring does actually match the base. So I'm using the outer circle, and so in order to get the area of the ring, I'm using the outer circle minus the inner circle, and the outer circle's area is going to be pi r squared. The inner circle's area, here you can see that the radius of the inner circle is y, and that's why we're using pi times y squared. And so if you take the outer circle and you subtract the inner circle having the radius of y, the outer circle having the radius of r, then what we're going to get is we're going to get the area of this ring over here. Okay, so that's what this represents over here. And now if I move to the next step, this is the key part for you to be able to understand. They now make the substitution. Instead of pi r squared minus pi y squared, we're substituting in h squared. Okay, so I'm going to come back over here and attempt to show you why that is going to be true. So I'm just going to clean this up a little bit over here, and then I'll show you a couple of different things. Oop, that's not what I wanted to do. Okay, so here what we have is, remember in the form where we are using this here as a radius, then we have established also that the height over here of my cylinder is also r, because it matches the hemisphere. That means that this height is also going to be r over there, and in this form this would also be r. And I'm highlighting that because what we're going to do over here is we're going to highlight the fact that if those are both equal, that is going to make this a 45-45 right triangle. That is going to be true no matter where we move it. And so in one of the others, when I move this down over here, keep in mind that this angle is 45, this angle is 90, and this angle therefore must be 45. And so for any of the heights that we use, okay, for any one of the heights that we manipulate up and down here, the length of the two legs of the right triangle in the figure on the right are equal to each other. That allows us to make the substitution for instead of y in terms of h. Okay, this becomes key, of course, because now when I factor out pi, I have the expression pi times r squared minus h squared, which of course equals the cross-sectional area of the hemisphere. And now that I've established those two things are true, the two cross-sections at height h are equal in area, and that means the two solids are equal in volume. Now let's look at the derivation of the formula. And so that allows us to do this. What I'm going to do is just capture that very quickly and show you a little algebraic manipulation to explain why that is going to be true. So I'll jump to the next page over here. And what we're going to do now is this. So we've got our formula over here. Let's just make that a little bit bigger. Okay. So first of all, this times by 2 is of course because we're talking about the volume of a hemisphere and we want the volume of a sphere, and that's why they're doubling it. This is the formula pi r squared h, which of course is the volume of a cylinder. But of course we know that when we are at the maximum height, then what we have at the maximum height is that h and r are equal, and so in the place of h we can sub in another r, and that of course is going to give us 2 pi r cubed. Similarly over here we have got the formula for a cone, 1/3 pi r 1/3 pi r squared. So that's the formula for our cone multiplied by h, which is the height of the cone. In the same way as we have for the cylinder, we can also for the cone conclude that h and r are going to be the same. And so if we substitute that r in over there, we get that. And what we end up is with 2 times 2/3 pi r cubed, which of course simplifies to 4/3 pi r cubed, which is the formula for the volume of a sphere. Okay, next one is a little bit quicker, a lot quicker. And so now I'm going to go over here, and what we're going to focus on over here is to try to use the formula 4/3 pi r cubed in order to help us to understand why the formula for the surface area of a sphere is 4 pi r squared. Okay, so we take a look at the sphere, and what we can do is we can take a slice of that sphere, and that slice is comprised of a bunch of pyramids. The pyramids have also got the formula 1/3 base area times height, and so what we can do with that is you can, the only other connection really that you need to make is that with these slices, these pyramids coming from the center of the sphere, each of the heights of the pyramids is in fact a radius of the sphere. Okay, which allows us to do the following. So all of them are going to have slightly different base areas, and if we let the A's represent those base areas, so base areas, because we're dealing with the same formula, 1/3 base area times height. So those are going to be all of our base areas. The total volume of the spheres will be the volume, the total volume of the pyramids will be the volume of the sphere. And so that gives us this expression, 1/3 base area times height, and we're adding up all the pyramids. That should give us the 4/3 pi r cubed from before. Now what we're going to do is factor out the 1/3 and factor out r. R, of course, was the one we replaced with the height. The sum of all of these base areas is, in fact, the surface area of the sphere. And so if we do a little bit of algebra, we multiply both sides by 3. We divide both sides by r. You should be able to see that what we're going to end up with is S equals 4 pi r squared, and again we divide both sides by r, multiply both sides by 3, and we end up with the sum of all of the areas equaling 4 pi r squared.